Francesca. Quindi non hanno sentito. Sono ma qua sai. Prova. Io questo sto usando. Ok. Okay, sorry. Okay. Good afternoon and welcome to our IAC seminars series. The speaker today is Dr. Francesca Pelusi, bachelor's and master's degree in physics at the University of Rome Tor Vergata. She has been a PhD student at the same university by discussing the PhD thesis on numerical studies on soft matter dynamics. The post-PhD activity started at first in Germany, where she stayed until the very beginning of 2023, by dealing with the wetting dynamics of droplets with applications in catalytic devices. Successively and until June 2024, she continues her activity at our CNR Institute IAC, placed in Rome, supported by Tech Starossa project and under the supervision of Dr. Massimo Bernaschi. Here she deals with the implementation of codes for numerical simulation and data analysis of complex fluids. Very recently and currently, she is still in our IAC Institute, but placed here in Naples as a fixed-term researcher supported by PNRR High Performance Computing Project, aiming to study soft matter properties using mesoscopic methods. Well, now I can leave the floor to Francesca. I thank you very much for your acceptance of our invitation, and I recall the title of your talk, which is Thermal Convection in Emulsions, Heat Transfer Properties and the Role of Droplets. Please, Francesca, and thank you again.
Thank you so much, Claudia, for the presentation. So today I would like to give you, hopefully, at least an idea about my research line that focus on the study of thermal convection of emulsions. In particular, I'm interested in the study of heat transfer properties and the role played by droplets, as we will see later. So first of all, this work started when I was a PhD student in Tor Vergata, but it is still an ongoing work. So I'm still working and collaborating with Professor Mauro Sbragaia and Roberto Benzi at the same university, but also Massimo Bernaschi and Andrea Scaglierini at the CNR. And there are other people that came abroad, for example, Matteo Lulli, now he's in China, and also Stefano Ascione that now is in France. And of course, there is always the presence of Sauro Zucchi in our works. So today, at the beginning, I will give you an idea about the material I'm interested in, so emulsions. I will give you a sort of list of the main properties of emulsions and why we study this kind of materials. Then I will give you information about the setup I'm interested in particular the thermal convection, specifically the really Benard thermal convection, but details will be given later. Just essential ingredients about the methodology. In particular, I used an open access code, a tier-defined code that we developed together in collaboration with people in Tor Vergata, me, Massimo Bernaschi, and other people. but just a brief idea about the methodology, and then I will go through the results and conclusions. So first of all, what are emulsions? So emulsions are part of a wide class of materials called soft materials that we can find in our ordinary life. So here, just an example is the foam of a beer, the gel, magma, the mayonnaise we use in our kitchen, and also the argil of the toothpaste. They are all examples. These materials have in common a long list of properties, but the most interesting one of the most interesting is their multi-component structure. So from the structural point of view, these materials are complex in the sense that they are composed by micrometric droplets of a given liquid component that are dispersed in another different liquid component. So you can think about something like oil and water emulsion, for example, is the most simple case we can think about. But one of the most interesting aspects is related to the rheological response. So with rheology, we mean the mechanical response of the material to an external force. So we apply a force and we want to know how the material reacts or behaves when we apply this external force. And the information, the rheological information, is drawn with this so-called rheological curve that relates the force applied for unit area, also called stress, and the velocity gradient that we can trigger inside the material upon the application of the force. So as you can see, emulsions present a complex rheology because if the applied stress is below a critical threshold, called the yield stress, it will be important in the rest of the presentation, then the material behaves in an elastic or solid-like way. It means that you apply a force, the material deforms, and then if you stop applying the force, it goes back to the initial condition. Otherwise, if you apply stress, meaning a force that overcomes the critical threshold, then it starts to flow as a liquid or a fluid. And this fluid behavior is well described by this phenomenological law of Herschel-Balchy. It's not important name, just to give you an idea about how we can estimate this behavior analytically, and the information about the threshold is included in this law. Okay, the yield stress is here. But the reason why we call it complex rheology is that if we compare the rheological response of a simple Newtonian fluid or homogeneous fluid, for example, the water, this behavior is linear, as you can see here. And it means that if you measure the viscosity of the material, that means the slope of this curve, then it's constant. It does not depend on the velocity gradient. Okay, it's always the same. And usually people call it as a Newtonian behavior. The viscosity is constant. Contrariwise, in the case of emulsions, we have a non-linear behavior with the presence of this threshold and this double behavior of elastic and fluid. But in the middle, there is something. It means that we can build or create an emulsion with a different droplet concentration. That means a different number of droplets. If I increase the number of droplets, then I'm increasing the droplet concentration, defined as the volume occupied by the droplets over the total volume. So by increasing the number of the droplets, then we can continuously move from a typical Newtonian behavior, so a linear behavior here, towards a non-linear behavior, up to the extreme case of a yield stress emulsion presenting a value of the yield stress different from zero. But there are some intermediate situations related to some intermediate values of the droplet concentration. So we can have a non-Newtonian behavior, non-linear, but at the same time, it is not yet enough concentrated to present a value of the yield stress different from zero. Emulsions find applications in a lot of contexts. Here, just a few examples: the food processing, emulsions, milk, and so on. But they are also involved in the production of paintings and coatings, or also during the oil recovery processes. And another very known example is the one of cosmetics and pharmaceutical products. Sometimes you hear about emulsions when you are just dealing with creams, and also detergents. But there are a lot of other applications not listed here, just to give you an overall idea. But now the question is, what is the origin of this complex nonlinear rheology that is different from the case? Oh, not yet. The video in the next slide. Too early, maybe. I just need to spend two words on the slide before, otherwise you cannot get the meaning of the video. No, the slide. But I just need to say something before in the slides. Okay. So we know that the rheology of emulsion is complex, as described before, but now we want to understand what is the origin of this complex behavior and what is the scale we need to investigate to answer this question. So first of all, obviously, it's not enough to describe the system with the continuous equation, so at the macro scale. It's not enough to just give an overall description of the dynamics of this kind of materials. But at the same time, if you go to smaller scale at the level of the molecules, in this case, there is too much information. That's not enough to see what is happening inside the droplets that have an intermediate space scale. So for this reason, what is convenient to do is to investigate the system at the mesoscale. So a scale that is intermediate between the macro scale, just the overall behavior, and the micro scale, just all the molecules are just investigating what molecules are doing at the same time. And at the mesoscale, what we know is that the fluidization mechanism, so the reason why we can move from a solid-like behavior to a fluid-like behavior, hinges in the occurrence of this so-called plastic rearrangement. They are a series of elastic deformation and plastic relaxation, and as there was visible in the video, if we can see it again. It's quite clear here. In this animation map, that is the output of one of my simulations, you can see that I'm not applying any kind of force, and the system is just rearranging in order to reach their more stable configuration. The reason is that imagine you have a single droplet or two droplets. In the case of two droplets, you have two interfaces. In the case of one droplet with the same volume as the sum of the two, you have just one interface. And the energy is proportional to the amount of interface. So the system tries anytime to reach its more stable configuration from the energetically point of view, and it means to minimize the interface area, minimize the energy. And this is the reason why the system tries to rearrange in order to minimize its energy, and this mechanism can be easily detected via this kind of plastic rearrangement, as you maybe observed in the video. Okay, you can see that locally there are this kind of rearrangement of droplets. And this is the mechanism why the system is able to move, fluidize, and so on. So we can go to the next slide. Great. Perfect. So up to now, we have something to remember that is helpful for the rest of the presentation. So what we learn is that if we are dealing with emulsions, if we want to know which kind of material we are dealing with, we need to know the value of the droplet concentration because it fixes the rheological curve, and it means that it fixes the mechanical response of the material. It's a kind of identity card of the system itself, because you can say, okay, if I have this emulsion with this kind of with this value of the droplet concentration, then I know how it behaves because I know which is the rheological curve. But at the same time, we also knew that the description has to be found at the level, at the scale of the droplet. So at the mesoscale, not at the macro scale, not at the micro scale, in the middle, just an intermediate scales. And now let's go to the setup we are interested to investigate. So we have emulsion, and we place the emulsion in a given setup. This setup is the so-called Rayleigh-Benard thermal convection. So as you can see here, we have the emulsion that is placed between two droplets, between two walls. One, the lower wall is hot and the upper wall is cold. So we have a temperature gradient between the two walls. And we have also the, and this system undergoes the gravity, okay? So we have a balance between the difference in temperature between the two walls and the buoyancy force acting on the system. Here the video helps in understanding why we call it thermal convection. This is what happens in our simulations. As you can see, we have droplets moving following the two convective rolls, okay, among between the two cold lower, cold hot upper and hot lower wall. Yes, and if we want to describe the dynamics of this kind of system at the macro scale, so with the continuous equations, we need the Navier-Stokes equations describing the dynamics of the fluid. It is not important to enter into the detail, just to give you an idea. And here we see that the temperature T affects the dynamics of the fluid. No, wait. But at the same time, okay, also the temperature follows its own equation. It is the advection diffusion equation, where the advection is given by the fluid. So there is a double coupling between the dynamics of the fluid and the dynamics of the temperature. How can we describe the system in this kind of dynamics? So the first important parameter is the Rayleigh number, that is defined as the balance between the buoyancy forces and the viscous friction of the material, defined in this way. So it's also related to the difference in temperature between the two walls. And it gives us an idea about the dynamical state of the system, in the sense that if the Rayleigh number overcomes a critical threshold called critical Rayleigh number, for this system it was around at 1,700, then we can observe the two convective rolls. And if we measure the kinetic energy as a function of time, the value of the kinetic energy stabilized again around the mean value. Otherwise, if the value is below the threshold, then it goes to zero. And it means that we are not able to capture the convective rolls. Nothing is happening. It's just pure conduction toward the system. And this is obviously what people did in the case of simple fluids, as in the case of water, with a linear Newtonian rheological behavior. And then when we know all the parameters of the systems that fix the value of the Rayleigh number, then we can measure the heat transfer across the system, defined as the total heat transport, meaning conductive plus convective heat transfer over the conductive one. So it is 1 plus something. It means that when the system is in a convective state, this term here is not negligible, different from zero, and then we have a value of the Nusselt number larger than 1. Otherwise, if we are in a pure conductive state, no convective rolls, then this term here is equal to 0, and the Nusselt number is equal to 1. So in principle, it is also a measure of the convective state. We know that if the Nusselt number is equal to 1, then we have conduction, no convective rolls. And if it's larger, we have convective rolls. But at the same time, the average value of the signal give us information about the amount of heat transported inside the material itself. So second checkpoint, we have 3 main parameters that will be used for the whole presentation. 2 of them can be used as input parameters. So if we fix the droplet concentration, we are fixing the kind of emulsion. And if we fix the Rayleigh number, we are fixing the setup, because here we have also the distance between the two walls, difference in temperature, characteristics of the fluid, the viscosity, and so on. So if we fix the Rayleigh number, we are fixing the setup. And then, as an output, we can measure the amount of heat transported across the system, so the Nusselt number. In this presentation, or better to say, in my research line, I investigated this landscape in 3 different times, exploring the parameter space in 3 different regions anytime. So as a first investigation, we considered situation just above the transition from conduction to convection, so just above the critical Rayleigh number, and situations where the emulsion is not so packed, it's not so concentrated, so just a few droplets, meaning that the behavior may be also non-Newtonian, so no linear rheological behavior, but not yet enough to show a value of the yield stress different from 0. Then we change the setup and the situation, and we have been interested in investigating what happens, again, just above the transition from conduction to convection, but in this case, we increase the value of the droplet concentration up to the emergence of a yield stress different from 0. And at the end, we explore the resting part of the phase diagram, Rayleigh number versus the droplet concentration, looking at what is happening if we increase the value of the Rayleigh number far from the transition from conduction to convection. In all cases, we were interested in measuring and investigating the heat transfer properties, and for this reason, we measured the Newton number as an output of the simulations. So we fixed the Rayleigh number, we fixed the droplet concentration, and we measure the heat transfer properties. With this aim, we employed a mesoscopic numerical method, so at the level, investigating the system at the level of the droplets. Just to give you an idea of the main ingredients of the model, 2 minutes. So we employed the open access TLB found code that has been developed from the collaboration with University of Rome Tor Vergata during my PhD studies with Massimo Bernaschi and other people and myself. And with this code, we are able to simulate 2D, so 2-dimensional emulsions using a mesoscopic description. And we have 2 main ingredients to take into account. So first of all, we need to create the interface in order to create the droplets. So we have we included in the model some interactions in order to start from 2 separated liquids and then observe the formation of the droplet. Okay, this is the first necessary ingredient. And then when we have 2 droplets close one to each other, we want to avoid the coalescence, so the merging of the 2 droplets together. That, as I said before, it's natural because the system tries to minimize the energy, but emulsions are such that the presence of surfactants in real emulsions, I mean, at the interface is able to avoid the droplet coalescence. And this is the only way to create a highly packed and emulsions at large values of droplet concentration, presenting a value of the yield stress different from 0. Otherwise, we will start with 1,000 of droplets, and at the end, you will see just 1 single droplet, which is quite big. So just to give you an idea about the ingredient that is necessary to avoid the coalescence of droplets, this is what happens if you do not include this kind of interaction. So when 2 droplets are one close to the other, then they should merge. Yes, the second one. But the second video for the same slide. Okay, thanks. But if you include this kind of interaction, you avoid the merging of droplets, and it is extremely necessary if you want to increase the value of the droplet concentration. Otherwise, just 1 single big droplets, because they are so close one to the other that it's impossible to avoid the coalescence of droplets. In nature, surfactants in emulsions play the role of the so-called disjoining pressure, that is this kind of interaction we include in our model. Just a few more words about the methodology. We have these ingredients, yes. Despite we are describing the system at the mesoscopic scale, at the same time we still have a double coupling between the dynamics of the fluid and the dynamics of the temperature. It is still there. Obviously, we are simulating the real situation. And then this code is also supplemented with some Lagrangian tools. Lagrangian in the sense that they are able to follow the dynamics of each droplet, not only the overall behavior, but also the single droplets. And it is quite performing since it has been written as a GPU parallelized code. So let's go to the first part of our first experiment. We are considering concentrated emulsions, so from linear to non-linear rheological behavior, but still not yet presenting a value of the yield stress different from 0, and we are just above the transition from conduction to convection, meaning that the value of the Nusselt number is slightly above 1, 2, 3, 4, okay, something like this. In this first experiment, we fix the value of the Rayleigh number, so the setup is fixed, and we vary the value of the droplet concentration by increasing the number of droplets in my system, and we compare the signal of the Nusselt number as a function of time. We capture from the signals both the average value, purple bullets here, and also the fluctuations that are reported in the inset here. So as you can see, the first thing that we can learn is that if we fix the setup and then we increase the droplet concentration, the average value of meaning the heat transport decreases as the droplet concentration increases, but at the same time, the fluctuations increase. And the most interesting part or aspect of this experiment was to understand why these fluctuations increase in the case of highly concentrated emulsions. So this is the first open question at the end of this preliminary work. And the second open question is what happens if we increase even more the value of the droplet concentration up to the emergence of a yield stress, because here we are dealing with non-linear behaviors, but not yet presenting a value of the yield stress different from 0. So to answer to the first question, we compared, and here we can also see the other video, a Newtonian emulsion. So it's the value of the droplet concentration is low. There are only a few droplets, and we compare the behavior of this kind of emulsion with the opposite case. It's highly packed, but not enough again to show yield stress different from 0. And maybe it's not so clear because it's too slow, but you can see that there are two roles of convective rolls, obviously. But qualitatively, we can see that there is a sort of breathing of the system, because there is motion and then it goes slower and then faster and then slower. And if we analyze the heat transport in this kind of material, and in this case, we compare the Newtonian emulsion, just a few droplets, with this case here, just to understand what is the role played by the droplets in the emergence of heat flux fluctuations. We can go back to the slides. In this case, we perform a different experiment. So we tune the value of the Rayleigh number in order to have a one-to-one comparison in terms of the heat transfer. So here there is the signal of the Nusselt number as a function of time for the Newtonian emulsion, this one, so it's diluted. And on the right-hand side, we have the same signal for the non-Newtonian emulsions. And you can see that the average value of the Nusselt number is almost the same. It's a one-to-one comparison between the two. So first of all, it's clear that in the non-Newtonian case, we have larger fluctuations of the heat transfer that are absent in the other case. And more, if we also compare to the case with no droplets, that is the dashed line here, the oscillations are completely absent. It means that no droplets, no oscillations, droplets, more oscillations. So the region, the origin of this fluctuation has to be found at the level of the droplets. The second aspect we learn is that if we decrease the average value of the Nusselt number, approaching the transition from above, because the transition corresponds to Nusselt number is equal to 1, as discussed at the beginning. If we decrease the average heat flux, then these fluctuations still increase. From the macroscopic point of view, what is happening to the system? Why we should have observed in the video this kind of breathing with motion, and then the motion goes lower and then faster and then slower. So when it goes slow, it means that we are considering, for example, one of the minimum of the signal. And in this case, if we measure the velocity gradient, the same appearing here in the rheological curve, we can see that the purple region corresponds to low values of the velocity gradient. So we are in this region here, and lighter regions correspond to larger values of the velocity gradient. So we are considering this branch here of the rheological curve. And it means that from the macroscopic point of view, what is happening to the system is that it is continuously transient from a predominantly elastic state. So the majority of the system is below the threshold, I mean. So the behavior is almost elastic. But then it is able to restart its move and go back in a more fluidized state that corresponds to the fluid branch of the rheological curve. Okay, we have this kind of transition that was clear from the video. But then we got that the origin of this fluctuation has to be found at the level of the droplets. And for this reason, we also define a value of the Nusselt number associated to the droplets. So from the knowledge of information about the droplets, center of mass position, and so on, we can define droplet Nusselt number similarly to what we do at the larger scale. So it's quite similar from here. So the difference is that at the macro scale, here we have an average on the whole domain. So we are considering a macroscopic observable. And in this case, we are just considering the contribution of each droplet. Indeed, if we sum up all the contribution and we average them, then we can go back to the macroscopic value. So with this information, we investigated the probability distribution function of this new observable at the droplet scale, at the mesoscopic scale. And here it is reported centered around the mean value and normalized with the variance. So you can see that if you consider the case with no droplet, so the system is exactly the same, the average value of the heat transport is the same, but then you can see that the probability distribution function has no tails. Okay, no extreme events. The same happens in the diluted case, Newtonian emulsion, empty points. As you can see here, they present almost no kind of tail, so there are no extreme events. Extreme events are visible only at larger values of droplet concentration, as you can see here. So fillet points for large values of the Nusselt number, 2.7, for example. But if you still decrease the value of the Nusselt number, then you have an increase of the tails of the probability distribution function. It is a proof, a measure of the it's a proof that the origin of these fluctuations that we see macroscopically as fluctuations in the Nusselt number have the origin at the level of the droplets, because also the droplets present these extreme events. Another proof is given by the correlation function between droplets. So if I have two droplets and then I want to know how much they are correlated and how much the correlation goes, how the correlation goes with the distance between the droplets. So in the case of Newtonian emulsion, the diluted one here, the droplets have a lot of space. They have the possibility to move. There is a lot of mobility. And in this case, obviously, the correlation drops to zero if the second drop is far from me, for example. But in the non-Newtonian case, then the correlation is still large also if the other considered droplet is far from me. And it is still related to the fluidization mechanism described at the beginning. So this plastic rearrangement, when the system is packed, it moves altogether there is a large correlation between droplets, and that's the reason why we have this kind of strange anomalous heat flux fluctuations. In another work, we also investigated the transition from the Newtonian case to the non-Newtonian case. So how is the situation in the middle if we continuously increase the droplet concentration from one to the other? And what we can see is that this transition is continuous as well. So by fixing the average heat transport and increasing the value of the droplet concentration, then also the extreme cases, the number of extreme cases increase as well. But we'll not enter more in detail on this part of the topic. So just a quick recap, we were investigating this region of the phase diagram, Rayleigh versus droplet concentration, just above the transition from conduction to convection, and for low values of the droplet concentration below the emergence of yield stress. And we found that the origin of this heat flux fluctuations has to be found at the scale of the droplets. So the presence of droplets is key in order to observe these fluctuations. And then there is the second question I left open at the beginning. That is, what happens if we still increase the droplet concentration up to the emergence of a value of the yield stress different from zero? Because up to now we were considering the diluted case and all intermediate case still non-Newtonian but not yield stress. So let's go exploring what happens again above the transition, but for emulsions presenting a value of the yield stress different from zero. And in this case, we focus, for example, on this emulsion here. It's quite packed, 0.8, so it's very close to 1. This is the initial condition. And first of all, we needed to be sure about the rheological behavior of the emulsion we were dealing with. So first of all, before applying the buoyancy, so placing in in a convective state the emulsion, we perform an experiment in order to extrapolate the information about the rheological response. So measuring the stress as a function of the velocity gradient in a situation where there is no buoyancy applied. And as you can see, we obtain a rheological curve that is quite similar to the one described at the beginning, so the Escher-Barkley law. We can fit it, and we also know the corresponding value of the yield stress that is different from zero in this case. In this work, we focus just on one value of the droplet concentration, so just one emulsion, and one kind of setup, so one value of the Rayleigh number. This is the initial condition. We still have a velocity gradient between the two walls and our initial condition for the emulsion. But what happens in this case? If we look at the signal of the Nusselt number as a function of time, we see that it doesn't go fluctuating around the mean value, at least not at the beginning, because there is this initial transient regime where it shows this kind of intermittency. So we have peaks, so-called heat burst, where the Nusselt number is different from 1, meaning that the system is moving in a convective state, but they are spaced out by some resting period where the Nusselt number is equal to 1. And if you look also at the thermal the situation of the temperature, you can see that there is no convection, just conduction. During this heat burst, what is also happening is that there are some coalescence events. It means that still we are including some interactions in order to avoid coalescence event. But if you apply an external force that overcomes the amount of interaction you are considering, then coalescence can occur as well. And this is what happens during these peaks of heat. And the occurrence of plastic event is changing the structure of the material. In the whole situation explored up to now, we were dealing with emulsions that do not change the structure. So they start just moving in a convective state. There is no variation in the number of droplets. So I prepare with the system with a number of droplets, and it is constant for the whole simulations. In this case, if we increase the value of the droplet concentration, this is not, it's impossible to place in motion in convection an emulsion with no structural variation. It's impossible. This is what happens. And this intermittent behavior, it's necessary to explore via numerical simulations because, for example, if you take just the continuous equations of the Navier-Stokes equation describing the dynamics of the fluid, and you include information of the Herschel-Barclay law, so the yield stress rheological behavior inside the Navier-Stokes equation, just in measuring the dynamical viscosity from the rheological curve, and then you place the information of the viscosity inside the Navier-Stokes equation, that's not enough to capture the restarting mechanism. So equations forecast just that if the system is stopped, it's not more able to be in motion again. Okay. Here the overall dynamics, but we can see also the video, just to give you an idea of what is happening. Not only looking at the signal of the Newton number as a function of time, but also what is happening to the emulsion itself, to these structural changes, and also the resting to heat burst transition. Okay, so here you can see that, for example, at this time here during the resting period, 2 bursts already occurred, so some coalescence event occurs through the system, so you can see that there are some bigger droplets that were not present at the beginning in the initial condition I showed you before. And anytime there is a peak in Newton number, then others occur. And at the end, if you want, you can go directly towards the end of the between 0.6 and 0.8. Okay, here is a resting period. You see that it's not really resting. Something is moving, even if we are not in correspondence of a peak in the heat transfer. But then, when the Newton number increases, we have a convective roll, and the temperature map is another evidence. So we have the thermal plume here. It moves with coalescence events. And then it goes back in a resting period, where there are no convective rolls here, but still there is a slight movement of droplets. Okay, and if you wait enough, and can we go directly towards the end of the video? Okay, what happens at the end after this number of coalescence event? What you observe is that a phase inversion of the original emulsion occurred. It means that if you start in you prepare a highly packed with a large droplet concentration of oil droplets dispersed in water, then at the end you will observe the opposite situation. You will have water oil dispersed in water, water oil dispersed in oil, water droplets dispersed in oil. Okay, and in this case there is also a region where you still have the original emulsion. So at the center of the convective rolls, you have the original emulsion, but a partial part of this emulsion undergoes a phase inversion. So you see here water oil that are water droplets that are dispersed in oil. Okay, we can go to the next slide. Here, just a summary. So this is the dynamics, what is happening to the emulsion. The structure is changing, and at the end we have a partial inverted emulsion. And when we reach this configuration here, it corresponds to a stationary state for the system because the Newton number fluctuates just a little bit because it's a diluted emulsion. We do not have anymore the original one. We have the phase-inverted diluted emulsion. By comparing the rheology of the initial condition, you can see that here we have oil droplets in water, and here we have water droplets in oil, partially. By performing again the rheological experiment with no buoyancy applied, you can see still the initial condition presents a value of the Hill stress different from 0, but if you perform the same simulation for the phase-inverted emulsion, it is diluted. So the rheological response is Newtonian, just linear with a constant viscosity. But the most interesting part is related to the restarting mechanism. So why the system is able to restart after a resting period where there is no convection, just conduction. The origin has to be found again at the scale of the droplets, and it hinges in the so-called the plastic rearrangement I described at the beginning of the presentation. Here I show you the same signal of the Newton number as before, together with the number of rearrangements. So with this kind of methodology, we are also able to detect the occurrence of a plastic rearrangement. We can count them. By counting them, you can see that there is a large number of plastic rearrangement during the heat burst, and it's obvious because the system is fluidizing, it's moving. But what is not obvious is the value of this plastic rearrangement during the resting periods. From the video, it was clear that during the resting period, the system is rearranging. It's not really quiet. I mean, something is happening. And what is happening is kind of a residual activity or microconvection of droplets that locally rearrange. And by changing locally the structure of the system, it finds the more convenient configuration to start moving again. And obviously, this kind of behavior cannot be captured from just using or just investigating the equation at the macro scale. If you look at the overall system, you are not able to capture this restarting mechanism. Other evidences, as before, the probability distribution function of the droplets, of the droplet Newton number, normalized as before. As you can see, large tails again during the heat burst, obvious, it is moving and it is highly packed. So the droplet concentration is large, the tails are large. That's expected. What is not expected is the large values of the tails in the case of resting periods. So during the resting period, we have tails up to 20 sigma, 20 standard deviations, as you can see here, and it is not expected, but it is the echo of this kind of microconvection and residual activity that is the origin of the restarting mechanism. Other evidence, again, the correlation between the droplets normalized, so the droplet correlation as a function of the distance between the droplets are normalized with the average droplet diameter. Again, the correlation is large during the heat burst, obvious. Unexpected is the large correlation during the resting periods. The correlation decreases when we when the system reaches a sustained convection, so after the transient intermittent dynamics, when it is stationary. And it is obvious because it corresponds to the phase inversion. So we do not have anymore the highly packed emulsion that we prepared at the beginning. So it is also expected. So just a quick recap of this second experiment. We investigated the behavior of emulsions presenting a Hill stress different from 0, and we are just above the transition from conduction to convection. We observed that the convective state is reached via an intermittent transient dynamics, and we investigated the origin of the restarting mechanism, that is this kind of residual plastic activity that is intrinsic in the nature of emulsions. But at the same time, if we want to observe a convective state in this kind of highly packed emulsions, it is necessary to trigger the phase inversion. It's impossible to observe a convective state without the occurrence of a phase inversion. So just to summarize what we did up to now, in the first two experiments, we are below the threshold. we varied in one case the real number, in one case the Newton number, but in both cases, in the first part of the presentation, there were no structural changes. In the last experiment, above the threshold, we observed, first of all, this intermittent behavior that does not appear in any other case, but also a structural change that we avoided to trigger in the. So in the previous two experiments, we wanted to preserve the structure of the emulsion we prepared at the beginning. In this case, it's impossible, as observed just a few minutes ago. So to answer to the last question, so what happens if we still increase the value of the real number? So we explore this region and this region. What happens if we go to larger values? Just exploring the last part of the phase diagram. So what happens is that we can, by tuning both the real number, so the setup and the temperature and the buoyancy and so on, and the droplet concentration, we have this phase diagram, and we can detect 5 different states. First of all, 2 of them are obvious. The first one is conduction, so below the critical threshold of the real number. So if you do not apply a sufficient buoyancy force, then nothing happens. We have the temperature that is still linear between the 2 walls, and nothing happens to the emulsion. The number of droplets is obviously the same. In the previous 2 experiments, we observed the so-called stable emulsions as stable convection, in the sense that we prepare the emulsion, we place it in the linear setup, turn on the buoyancy force, and we are able to observe the convection. But the convection does not affect the structure of the emulsion. Indeed, if you measure the number of droplets, it doesn't change in time. But if you still increase the buoyancy, you increase the external applied force, then you can observe other kind of states. The last one is well known, already discussed, the phase inversion. So if the droplet concentration is so large, like in this case here, and you increase the external force, then you just observe the rupture of the emulsion in favor of the phase inverted one. And these 2 intermediate cases are the breakup dominated case. So we have a sufficiently moderated packed emulsion, but still diluted. Then we increase the value of the applied force, and we observe at the end a convective state. Here we see the plumes in the thermal map. But it's enough, we are shaking too much the system up to the case we are breaking up the droplets in smaller one. And it can be seen here because the number of droplets increases as a function of time. So from 1 we have 2, from 2 we have 4, and so on. And for this reason, it increases. Something is changing, the structure is changing. At the same time, we have also the opposite situation, the situation where we we apply the buoyancy force, we observe convection, so it's a convective state as well. But we have coalescence events instead of the breakup, the opposite case. So from 2 droplets, we have 1, and so on, and the number of the droplets decreases in time. So this is the landscape, the overall scenario of this kind of dynamics, emulsions under really benign thermal convection. In the phase diagram of the Rayleigh number as a function of the droplet concentration, we can observe that by tuning or fixing the 2 values, then we are in one region or in another one. For example, here is evident how the threshold to trigger stable convection increase by increasing the droplet concentration. It means that if we want to place in motion our emulsion, you need to push more if you have a larger number of droplets. And then we see that if you apply very large buoyancy forces, then you can go or in a breakup dominated case, so you are shaking too much, or in the phase inversion one, if you are at large or low values of the droplet concentration. All experiments explored before lies here. So just as you can see, again, just above the transition from conduction, gray region, to stable convection, so the light blue region. In this work that has been just submitted this morning, so we also had to characterize the emulsions from the beginning. So we are changing the value of the droplet concentration. We want to be sure what is the identity guard of the emulsion. So what is the mechanical response? Again, rheological curve in this case. We perform this dedicated experiment, and we measure it for all emulsions. And we can see that we are really moving from or varying the droplet concentration from a Newtonian behavior with a linear rheological curve towards non-linear behavior up to the emergence of the yield stress in the most extreme case. But what happens if we go to larger value of the real number and we observe these three different possible states, the one with the dominated by breakup of droplets, the one dominated by coalescence, or the one dominated by phase inversion? What you can see is that the rheological curve changes in all cases. Obviously, in the first case here, usually emulsions lying in this region are diluted, or so the value of the droplet concentration is low or moderate, and also the original emulsion present a Newtonian linear rheological behavior, and it is still Newtonian, and that's fine, expected, I mean. What is not expected is that if you increase the value of the droplet concentration and you measure the rheological curve at the end of these simulations, so we have structurally different emulsions in this case as compared to the one prepared at the beginning. And what you can see is that the rheological curve is always linear. It means that if the emulsion undergoes a structural variation under thermal convection, what happens in any case is that the rheological behavior moves from a non-linear or also yield stress towards a linear behavior. It's a drastic change in the response of the material. We also study the heat transfer properties. Here, the average value of the Nusselt number as a function of the Rayleigh number for different values of the droplet concentration increasing in this direction. The last two corresponds to yield stress emulsions. And what you can see is, first of all, that the threshold, so the amount of energy, the amount of the buoyancy force you need to apply in order to trigger convection and have a Nusselt number different from 1 is shifted by increasing the value of the droplet concentration. Here is for the diluted case is almost 10 to the third, but if you go, for example, around 0.7, it's here around 5, 10 to the 4, for example. Okay, it is shifted. And another evidence is that if you investigate yield stress emulsion, as discussed before, you do not see a smooth trend. So the Nusselt number does not increase smoothly with the Rayleigh number, but what happens is that there is a jump. It's a sharp transition, and it is related to the phase inversion that is occurring inside the material. Okay. Phase inversion means that I do not have anymore the oil in water emulsion, I have the water in oil emulsion, but the amount of oil and the amount of water was the same as the beginning. And the phase inverted emulsion will have 0.16 instead of 0.84, for example, in the droplet concentration. And the behavior indeed is quite similar to the diluted cases. But another interesting experiment we performed was that, okay, we started with this kind of emulsion here, highly packed. We increased the Rayleigh number, so we are moving along this direction, along here, fillet points. And then we observe, okay, convection associated with the phase inversion. But what happens if we do the opposite? So we start from with an initial condition that is already phase inverted, and then we go back with the value of the Rayleigh number. And what we observe is that the curve changes as compared to the previous one, going back in this way, presenting. This means that there is a high hysteresis behavior. And what you can see here is that it's impossible to go back to the initial condition. If you phase inversion occur, then you are not more able to go back. As a last result, just to give you an idea, we also investigated, we compared, in the case of large values of the Rayleigh number, the breakup of the dominated case and the phase inverted one. So we are just looking at the upper part of the phase diagram. And we measure the probability distribution function of the average radius of the droplets are here. So you can see that in both cases, if you are diluted or if you are highly packed, in both cases you will see a shift in the average value of the probability distribution function that is reported here, the mean value of the radius as a function of the Rayleigh number. If you increase the Rayleigh number, so moving from in this plot from the right to the left, then you can see a decrease in the value of the Rayleigh number because you are in the value of the average radius, because you are shaking even more and you have just the breakup of droplets in both cases. So you will see the decrease in behavior that is with a power law that is similar in both cases. So it means that if we look at this in this part of this phase diagram, if you have a breakup dominated case or a phase inversion, the overall behavior is the same, but these two curves are shifted because the initial condition to reach that state is different in two cases. So this is the reason why you cannot match the two in one. So last breakup, we also explore the upper part of the phase diagram, and we had at the end the overall scenario clear. We answered the question, what happens if we increase the Rayleigh number? We observed that there are some possible different dynamical states for the emulsion, with or without the rupture, with or without the coalescence or phase inversion. So there are structural changes that affect both the rheological behavior, because from nonlinear we move to linear emulsions, but at the same time also the heat transfer properties. Going to the conclusions, by placing all together the three experiments discussed, we completed the phase diagram and the scenario Rayleigh versus number of droplets for droplet concentration. We studied emulsions in this kind of setup, so Rayleigh binary thermal convection between two walls. The lower wall is hot and the upper is cold, so it's similar to the case where when you are boiling water to cook pasta, let's say. And we investigated the three cases. In the first one, so non-yield stress emulsions, so emulsions with no yield stress. Then we investigated the fluctuations, and we found that the origin has to be found at the level of the droplets, and it is due to the presence of these finite-sized droplets in the emulsion. If we increase the droplet concentration, we first observe the intermittent behavior. The restarting mechanism is due to this plastic rearrangement that are intrinsic in the fluidization mechanism of the emulsion. But we also observe that if you want to place it in a convective state, then you need to trigger the phase inversion. That's no way. And at the end, we completed the scenario looking at all possible structural changes occurring by varying both the buoyancy force via the Rayleigh number from the one end, and on the other end, the droplet concentration. With this, if you are interested or curious, you can see also more than what I explained today in our publications, but I'm here and happy to answer your question if you have any. Thank you so much.
Okay, Francesca, many thanks for your very interesting and clear talk. Okay. Are there some questions or comments here, or do you have? Okay, Francesca.
Just one question. What about the 3D simulations? Have you tried 3D simulation? And related to this, there are some comparison with experiments, validation by physical experiments.
The point is that it's not so easy to perform this kind of experimental counterpart is not easy to produce. So for the moment, there are not so many experiments on this topic. What we expect is that if we increase the dimensionality, that was something that we are working on right now. So we are trying to extend our 2D code in 3D code. It's an ongoing work. But we expect that qualitatively, the phenomenology doesn't change, but maybe the numbers, yes, of course. For example, the exponent of a scaling law may change if you change the dimensionality, but not the presence of the scaling law. This is qualitatively what we expect. So the phenomenology is still there. Maybe, obviously, the number will change. Numbers will change, but not the phenomenology.
Just a curiosity about the time scale of the simulation, and also there is the time of calculation for the simulation. How long?
Do you mean the
How many time
human time or machine time?
And simulation time.
Okay.
Also the computer time of the
So,
simulation.
so for example, the simulation with the intermittency required 10 millions of time steps to reach the stationary state that is the one at the end, and the whole dynamics cannot be reported in this scale. So we had to wait a lot, and it required something like at least 2 or 3 days of human time. And to have a one-to-one comparison between simulation units and real units, you need to fix some parameters in the system. So, for example, you need to fix the viscosity, which is the value of the viscosity we are simulating, and so on. So the most simple thing we can do is just to talk about the simulation units. But obviously, we can always go back to the real units. And that's all.
I have two questions for you. Both on the slide 34, probably.
Yes.
Concerning the intermittency phenomenon you described, here it is observed for given values for phi and for the real number Ra. So the first question is if you can observe the same phenomenon or some phenomenon of this type with different values for phi and for real number. And the second one is what happens if you change the initial conditions? In other words, if you have some similar phenomenon by changing the initial condition. Thank you.
Yeah, that's a good question, because maybe some of you could think that it's just an artifact or numerical artifact. So maybe it just create, numerically speaking, this equation to observe this kind of phenomenon. But we verified it. I can go to breakup slides. Okay, here, for example, you can see that by fixing again the value of the droplet concentration, so the same as discussed before, the purple signal is the same shown before, showing intermittency, as you can see. But there is, it's a narrow range, but it's a finite range of value of the real number where you can observe, you can still observe the intermittency, as in the case of the green signal here. But if you go just below this range, then you will see nothing. So just conduction. The signal is the black one, is reported behind, so you can see that's here, and it's placed for a value of the Nusselt number equal to 1. So it's just conduction. And if you still increase a bit, you overcomes the range, and then you observe suddenly the phase inversion at the beginning here. So you can see that the Nusselt number is just different from 1 from the beginning, and it means that here already occurred the phase inversion, and you are not able to see the intermittency. So it's a narrow range, but it's different from 0. And we also try to change the droplet concentration and see if it persists or not. And what we observe is that if you increase a little bit the droplet concentration, this is the one reported in the previous slides, you can still capture again the intermittency. It means that it's not just a matter of numerical simulations, but it's a real phenomenon. And it has been also verified, to answer to your second questions, by changing the initial condition, because you can think that always is related to the initial condition I choose at the beginning, but it is not true, because if you try to prepare the emulsion in a different configuration, okay, same number of droplets, so the droplet concentration is the same, but you change the disposition of the droplets. You are changing the initial condition, and as you can see, obviously you do not capture exactly the same because the initial condition is different, but still we have the evidence of this intermittent transient dynamics here, and then it starts convecting as a phase-inverted emulsion as observed in the previous case. So see, our result is robust in this sense. Yes.
Okay, thanks.
Okay.
Are there other questions? Okay. Mario.
Thank you, Francesca, for your very interesting talk. I just have a question related to the mathematical stability analysis of the conduction equilibrium of the conduction solution, because it happens that, okay, you have conduction, then you are saying that you have convection before conduction, then you have losing of stability for the conduction solution, and then there's the onset of the convection solution,
yes.
Right? Yeah, but is this transition sharp? Because usually you have that for the Rayleigh number, if I'm not wrong,
yes.
You have two different regions, convection and conduction, that are not so sharply divided. I mean, that's why because you have the onset of oscillating modes when you analyze so you have, maybe with linearization, you have a lower bound for the critical Rayleigh number.
Yes.
Then by studying with Rionero's approach or something like the Lyapunov approach, then you have an upper bound for the instability region.
Mm-hmm.
And maybe there's a gap in between these two regions. And that's why you are experiencing that kind of oscillations. Because you have stability below.
Oscillations in the Newton number, you mean? Which kind of oscillations?
Yeah, in the behavior, because you do not have sharply separated conduction and convection. You still have a transient between them. Mm-hmm. When you analyze for different Rayleigh number, the behavior of the solution.
Like in this case, yes.
Yeah. So my question was, did you perform stability analysis for the stationary solution, for instance, or nonlinear analysis for the model?
No, we just performed some, let's say, phenomenological experiments in order to be sure we were simulating the correct physics. So textbooks, we know, say that, okay, if you have this kind of system with this and this ratio and so on, with this kind of setup, you should detect the value of the critical real number that is around 1,700, for example. And we performed this benchmark for the coding. If we were able to reproduce what is known in the literature, we were sure that the simulations are trustable. I mean, this was the only stability analysis we performed, the only phenomenological analysis. Was it? Nothing analytical, I mean.
Thank you so much.
Thank you for your question.
Okay, I don't see any question here. Are there other questions, comments? No? If not, well, we thank you again.
I thank you so much for...
Okay, and we'll see for the next seminar of our series.
Okay.
Okay,
Good afternoon.
good afternoon.